Hello, this is the next video in a playlist that I'm calling Complex Variables, where we're going to have an in-depth analysis of complex variables or complex analysis. And the first component of this playlist is complex numbers. So let's jump to today's topic, which is the complex exponential function. And the goal is to define e to the z, where z is a complex number. So first, let's examine a Taylor series for e to the x. And you always how far back do you go in theory and development? And at some point you have to cut it off for the length of the video. And so we're going to assume you're familiar with Taylor series. And so a Taylor series of e to the x expanded about zero, or more specifically a Maclaurin series, can be represented like this. Now if we take every other term, so we take the even terms and then the odd terms. I say odd because it's raised to the 1, raised to the 3, raised to the 5. The exponent's odd. Okay. Can be rewritten in this fashion. So now what we do is let's replace x with iy, where I is an imaginary number, in e to the x. So e to the iy. So that means you put in iy wherever there's an x. So this line becomes here, right? We're just putting iy. But then we separate them into the even exponents and odd exponents, right? One is, a number raised to the 0, so it's an even. But then when we distribute the square, so it's I squared y squared, but I squared is -1. So that's how we get this term. And here I to the 4th is 1, so it becomes positive. I to the 6th is I to the 4th times I to the squared. So you get the negative, and then it's positive, so you get alternating signs. But now let's look at this term. So iy comes down, iy to the 3rd. So of course we get y to the 3rd, but I to the 3rd is minus I, which is this. And I to the 5th would be I to the 4th times I. So you get plus I. So this term is here. Well, and then each term, alternating signs. But the top expression is an expression for the Taylor expansion of cosine. So this is exactly the cosine of y. Now, if we left factor out an I in these terms, then what's left is the Taylor expansion of sine of y. So e to the iy is cosine of y plus I sine of y. So it's a complex number. Now let's evaluate e to the iy. So the minus goes into the y. So we just use this expression again, but then we put in minus y in these terms. But cosine is an even function, so you just get cosine of y back. Sine is an odd function, so you can bring it out front, and that's it. So e to the minus iy is cosine of y minus I sine of y. Now notice that they're very similar except for this symbol. It's plus here and a minus here. Well, that's what a complex conjugate is when you change the sign of the imaginary opponent. So that means the complex conjugate of the e to the iy is e to the minus iy, right? The complex conjugate is minus iy. Now, let's evaluate e to the iy at y equal pi. So that means we were evaluating e I to the pi. So that means you put in pi. Cosine of pi is -1. Sine of pi is 0. So we get -1. And we can also think about it like this. Cosine of pi is -1. But if we subtract 0, we're not changing it. Sine of pi is 0. But this is e to the minus I pi, right? And so they're both -1. And it sort of makes sense because, first of all, they're complex conjugates, but this is a real number. And so changing the sign of the imaginary component, which is 0, doesn't change. So they are complex conjugates. So here we're going to add 2 and 3. So this is the expression in 2, and this is the expression in 3. If we add these components and then back solve for cosine, we get this term. So cosine of y can be represented in this complex form. Then we can also subtract these two equations and then back solve for the sine of y. And sine of y can be represented like this. Now, here's a tidbit that we'll prove in a later video. But if we divide the cosine of y, divided by the sine of y, that's the cotangent of y. So we can get an expression for the cotangent of y. Then we can substitute the arc cotangent of y in place of y, and then you can back solve for the arc cotangent or the inverse cotangent of y in terms of this complex expression. Now we're not doing it, but I'm foreshadowing. I'm going to use a property in an example later in the video, but this is how it's done, and we'll derive it exactly in a later video, but I can't because of the interest of time. So let's evaluate these two expressions, e to the iy, sub 1, e to the iy sub 2. So we look at them. Now we put them, this is their complex form here, but in a previous video we showed how to multiply complex numbers, and it's literally you or multiply. So you multiply the modulus, which is 1 in both cases, then you add the angles, and this is it. But this is an expression for e to the I, y1 plus y2, and it can be thought of as this. So here, when we're raising e to the thing, we can add the exponents. Now let's look at e to the z, where z is a complex number, x plus iy. Well, we can separate that in e to the x, e to the iy, but e to the iy is the cosine of y plus I sine of y. So this is the expression of e raised to a complex number. So the modulus, it would be, the radius is e to the x, and if you look at it in polar form. So z, let it be a complex number in the real and imaginary, or in polar form, where n is a integer. And if we look at z to the n, now z, of course, in polar form is this, raised to the nth power. So then we can distribute the n, but e to the I theta, this is part of de Moivre's theorem, where you just take it times the angle. So e to the I n theta. And so a complex number raised to the z can be thought of as this, r to the n, e to the I n theta. Now let's go through some examples. So let z be a complex number. Show that z raised to the ei alpha, where alpha is a real number, it's literally a rotation of z by angle theta. So this complex number can be thought as a vector originating at 0, 0 and then out to this complex number. And then it creates an angle with the real axis. But if you rotate it, literally keeping the anchor at 0, 0 and just rotating it an angle of alpha, that's what this represents. It's a rotation of z by an angle of theta. So z, e to the I theta, well, z can be thought of as this in polar form, where we add the exponents. Well, and this is a new complex number with angle theta plus alpha, which means it's a rotation. So let's show that e to the I theta is equal to e to the I theta plus some multiple, integer multiple of 2 pi. Well, if we look at e to the I theta 2 pi, that's the cosine of this plus I sine of this angle. But whenever you take the original angle theta and then you add a multiple of 2 pi, you're just literally going around the circle and coming back to the same spot. So it doesn't change this expression. So it's really the same as the cosine of theta plus I sine of theta, same as sine. But that's e to the I theta, and that's what we wanted to show. Now let z be a complex number, and we want to find the modulus of eiz, where z is this complex number. So the modulus of e to the iz can be written like this. Iz means you take I, and this is z, the complex number. Then you distribute the I, and then you get this term. This becomes negative r sine of theta, and this is it. We separate the exponents in e to the minus r sine of theta, e to the this piece here. This is a real number, so the modulus is just a product. But the modulus of this, you end up being, so this is a sine of an angle, r cosine theta, plus I times the sine of this angle. But the modulus means you square those, so you get cosine squared plus sine squared, which is 1. And then this is a positive real number. So that's it. And so this is the modulus of this number, e to the iz. So if we look at a quick example of using this result, we have the complex numbers 6e to the I pi over 3. We want to find the modulus of e to the iz. Then we can just use this formula, and it's e raised to the minus 6 sine of this angle pi over 3. Sine of pi over 3 is radical 3 over 2, and then this reduces to e to the minus 3 radical 3. And so this is the modulus of e to the iz. So let's look at this. So let's find this complex number where it is the addition of two complex numbers. Now I'm foreshadowing here because when you add numbers, you can really think of it as a parallelogram, and then this will play a part when we look at the dot product and cross product of complex numbers in a later video. I think it's like 3 or 4 videos from now. But if we have a complex number, say z1, and we have another complex number z2, when we add them, you can think of it as taking this piece and putting it on the end of that, and then that becomes the addition, z1 plus z2. But let's write what the general expression for z1 plus z2 is. Now, to do that, this is the 0, or this is the real axis here, and so to do this, we need to find this angle and this distance here. So this modulus of this, or the radius of this, the length of magnitude of this line, is, we use Pythagorean theorem. So the height of this, so the imaginary height plus the real squared, sum squared, taking the square root, is the length of this. So that's what we get here. So this number is the addition of these two vectors, right? You add the real components plus you add the imaginary components. So this is the real component, this is the imaginary component. So the modulus, or R3, is the square of this plus the square of the imaginary component, square rooted. But if you square this and square this, it boils down to this. So at some point you get cosine squared, sine squareds, and those are ones, and that's what this is. But then the cosine of the difference of this angle actually is a trig identity that you have to use to simplify. And that's it. So that's the generic radius of, or the modulus of this new complex number, or the addition of two complex numbers. And if we look at the angle, so if we think of this as a right triangle, and this is the angle, so tangent of theta would be the imaginary divided by the real component. And so the tangent is the imaginary length divided by, the real number. And these are both real numbers, right? If you just look at that imaginary component. But then you can back solve for theta 3 by taking the arctangent, or the inverse tangent of both sides. And then we put in what the real component is, and the imaginary component here and here. And that's it. And so this is the theta, this is the angle. So this expression here, R3, is this. R3 is this number, and then the angle, of course, is this number. And we have one last example here. So P and M, real numbers, we want to show that this crazy expression is 1. And to me, it's kind of a mind-blowing result to think about it. But we'll do it in steps. We take this expression on the left, bring it down. And remember earlier in the video, I rewrote something, or suggested that the inverse cotangent, or the arc cotangent, has an identity. And we use that here. So everything else just copies over. And this is the arc cotangent of P, which is a real number. Well, Here the 2's cancel and I times I is -1. And so we're left with minus m of this. And this expression, we write it as e to the log of that. But since it's e to the log, the m can come out front. And since it's the same base e, we can just put it in the exponent. Well, we have this number minus this number. Well, it turns out p minus I, p plus, divided by p plus I, is 100% the same as pi plus 1, pi minus 1. Now, I'll let you do the long division of that. Not long division, but the division, which we covered in a previous video, dividing two complex numbers. They're 100% identical, which to me is kind of cool in itself. So we have a number minus the same number, which is 0. E to the 0 is 1, and that's what we wanted to show. Okay, well, I'm running a little bit long, so I'm going to cut it off here. The next video is complex quadratic equation with complex coefficients. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.